All right, good morning, everybody. So, no quote of the day for today. We're going to jump right into it because we have quite a bit to get through today. So, the plan for today is to continue with Chapter 7 on factoring. Last time we introduced the idea of factoring trinomials uh, of this form, ax squared plus bx plus c, so quadratic expressions where the leading coefficient, the coefficient on the x squared term, is not 1. So we saw the AC grouping method, as well as kind of a guess and check method. And today we're going to move on to 7.4, factoring special products. So a few wrap up examples from section 7.3 and then on to 7.4. Okay, so let's take a look at, just to kind of remind ourselves of the AC grouping method, let's take a look at this problem. 3x squared plus 5x plus 4. This might be a candidate for guess and check, but let's go through the full AC grouping method. So we see that A equals 3, C equals 4, so AC equals 12, and B equals 5. So I'm looking for two numbers that multiply to 12 and add to 5. So we've been calling them M and N, and I can make 12 by having 1 times 12, 2 times 6, 3 times 4, or if I keep going, I get 4 times 3, that repeats. So I'm looking for two numbers that multiply to 12 and that add to positive 5. Remember, my goal is to break this 5x into plus mx plus nx. So that's really my goal. I need two numbers that add to 5. So I know that m and n have to both be the same sign. They could both be positive or both be negative to satisfy the constraint that their product is 12. But they have to add to positive 5 and they have to be the same sign. So they both have to be positive. And actually, if I look through my list over here, I actually don't see any way to split this middle term, this 5x, up into the two terms whose coefficients multiply to 12. So if I check my work, just double check A is 3, that looks right. C is 4, that looks right. AC is 12. How can I break down 12? 1 times 12, and 2 times 6, 3 times 4, that all looks good. I'm looking for, and I know that they both have to have the same sign, so both positive, both negative. I'm looking for them to add together to make positive 5, so both would have to be positive. And I don't see 1 plus 12 is 13, 6 plus 2 is 8, 4 plus 3 is 7. None of those are 5. So I actually noticed that I was going to write an X here, but I'll do it like this. I can't find a way to break that 5x up in such a way that I can proceed and do my factoring by grouping and get a factorization of this. It turns out that this quadratic is prime. And we call it prime because it's kind of analogous to the idea where, say a number like 18, I could break it into like 2 times 9 or 2 times 3 times 3. But a number like 7, well, I can't break it into any more interesting factors than just 7. It's kind of just itself. It's, in a sense, kind of a base unit, a base building block. So we would call this a prime number versus a composite number that has some factors inherent in it. And similarly, we would call this a prime polynomial because it can't factor. Okay, let's look at this next example, 6x squared plus x minus 22. Oh, also, as a quick aside, if we tried to use the guess and check up here, it would be very muddy, very murky, right? Because I don't really have an algorithm with a set a set number of steps, I have just kind of like guessing what my first parentheses or second parentheses are going to look like. I'm trying some different things, and if I try a few things and they don't work, did I just not think to try the right thing yet, or is there no way to make it work, right? So if I use the guess and check method, it can be tough to figure out if a polynomial is prime. But going through the AC grouping method, I've effectively proved that this polynomial is prime, that there's no way that I can factor it into a product of two linears where my coefficients are all integers. So that's a benefit of the AC grouping method as well. Okay, but this next problem, 6x squared plus x minus 22. Again, a is 6. C is negative 22. AC is negative 6 times 22. I'm going to leave it like that. So I'm looking for two numbers m and n that multiply to negative 6 times 22 and that add to positive 1. I'll put the plus 1 there just as a reminder that I want a positive 1 for their sum. Since I already have this factored a little bit, I left it as negative 6 times 22. And I can actually factor it a little further. Negative 2 times 3, that's for that 6. And then 2 times 11 for the 22. Sometimes if I break my number down into its prime factorization, it makes it a little easier to go through this process. So I have 1 times 6 times 20 is 120. 6 times 2 is 12. So I think that's 132. 2, well, if I use this 2, this factor of 2, that leaves me with 2 times 3 times 11. I'm not worrying about the sign right now, just the numbers. 2 times 3 times 11, so that's what, 33 times 2 is 66. Does it have a factor of 3? Yes, it does. If I use up that factor of 3, that leaves me with 2 times 2 times 11, or 44. Can I make a factor of 4? Well, yeah, I can. I can combine this 2 with that 2 to make a 4, leaving me with 33. So 4 times 33, leaving me with 11 times 3. Is there a factor of 5 in here? Well, no. 5 is a prime number. There's no 5 in the prime factorization. How about 6? Well, yeah, I could use, say, this 2 times 3, leaving me with 2 times 11, or 22. 6 times 22. What about 7? 7's prime, so no, I don't see that in the list of prime factors. How about 8? That would be 2 cubed. I have 2 factors of 2, but I don't have 3 factors of 2. 9, no, that doesn't, I don't have a second factor of 3 to make a 9. 10 would need a factor of 5 to build it, but I don't have any factors of 5. 11, okay, I have 11 times 2 times 2 is 4, times 3 is 12. And then, of course, if I go up to 12, I get 12 times 11. I've repeated. So I actually have quite a few ways of making a product that multiplies to A times C. I know that A times C is a negative number, so I have to have opposite signs. One has to be positive, one has to be negative. I know their sum has to be positive 1. So the positive has to go with the larger number in magnitude, the negative with the smaller number in magnitude, so that when I take the positive plus the negative, I end up with a net positive. So opposite signs and positive on the bigger number. So I'd have to have like the positives going down here for n and the negatives on m. And I want these with the signs to add to positive 1, or I'm looking for two numbers in absolute value and magnitude where the difference looks like 1. And I see 11 and 12 seem to fit the bill. So m equals -11, n equals +12. And again, what's the purpose of doing all of this? It's to say, how do I break up my middle term here? So I have 6x squared. Maybe I'll do plus 12x minus 11x minus 22. So all I did is rewrite plus 1x as plus 12x minus 11x. And you might say, oh, well, I could have figured this out at the beginning. Well, why couldn't I have written plus 2x minus 1x or plus 20x minus 19x? Well, those would have all been valid algebraic steps. You could have written another line like that and it would have been equivalent, but where do we go from here? We've broken this up in just the perfect way. I don't want to separate this negative too much there, but we've broken this up in just the perfect way that if I look at my first two terms, and if I look at my last two terms, I have a common factor in each of those sets of two terms. And when I factor, I will be left with another common factor that I can then factor out. So out of these first two terms, I can factor out a 6 times x, and I'm left with x plus 2, 6x squared plus 12x. Out of these next two terms, I can factor out a -11, and I'm left with x plus 2, and I note that I'm left with this common factor of x plus 2. That is the reason that we went through so much trouble to figure out exactly how to break up this middle term. We broke it up in exactly the right way that when I take the first two terms factor, the second two terms factor, I'm left with, again, a common factor. I pull this x plus 2 out, and I get x plus 2 times 6x minus 11. If I FOIL, first gives me 6x squared. My outside gives me minus 11x. My inside plus 12x. That nets to plus 1x. And my last give me -22. So that looks good. So this is, this was not at all a trivial problem to do. We had a lot of different ways to factor. We had to think through the signs carefully and so on. There were a lot of steps, but these are the same steps every time. That's really the benefit of the AC grouping method as compared to, say, a guess and check method. The cost of the AC grouping method is sometimes for an easy problem, the guess and check method is much quicker, much less cumbersome. And the AC grouping method is kind of, always more or less the same amount of steps. And then let's look at one last example, and then we'll do a few examples on the worksheet. So here we want to factor 6x squared minus 46x minus 16. So again, we have a equals 6 and c equals -16. We see here we really have a lot of ways of factoring a and c. So we'd have to consider, if we were to do guess and check, we'd have to consider one structure that looks like x versus 6x, and one that looks like, say, 3x against 2x to make the first term work out. And then for our last, we could have like 1 times 16 or 2 times 8 or 4 times 4. That's just a lot of different permutations. There could be pluses and minuses everywhere, right? Some of the terms in the original expression are negative. So this is definitely one where I want to use the AC grouping method and go through systematically, because just the number of things I would have to try to go through a guess and check or trial and error method, it would probably take me a lot of time and effort and frustration. So I see that a times c is negative. What's -6 times 16 but I'm going to write that as -2 times 3 for the 6. And then 16 is 2 to the 4th power. So I have 4 factors of 2 coming from that 16. And remember that I'm looking for two numbers that multiply to a times c and that add to b, which is -46. So I'll start listing out my m and n that multiply to 6 times 16. So this gives me 1 times, well, what's 6 times 16? I think that is 96. I can think of it as 6 times 10 plus 6, so that's 60 plus 6 times 6 is 36, 96. 2 is definitely a factor. If I get rid of this 2, I have 2 to the 4th, or 16, times 3 is 48. 3 is a factor. If I get rid of this 3, that leaves me with 2 to the 5th, or 32. 4 is a factor. That gets rid of 2 of the 2's. And I have 2 cubed is 8, times 3 is 24. Kind of as an aside, students often ask, oh, well, we have access to calculators all the time on our phone, on our computer, all of this. Why do I ever need to know how to multiply numbers in my head or something? Well, if you have to do all of these calculations on the calculator, I mean, all of these, like, what's 2 to the 5th is 32, or, what 2 cubed times 3 is 24. If you have to do all of these on the calculator and not in your head, it just takes so long. It takes, probably 2 to 3 times as long to go through a problem like this. So a problem that might take 2 or 3 minutes becomes a, 8 or 10 minute problem. So, I mean, that's one reason. So if you're, not comfortable with times tables and things, or doing this work in your head, that's a good skill to practice. I don't design the exams with the intent for time to be an issue, for time to be a factor. But that being said, if you're working at a pace that's half or a third as fast as I would expect you to work, time can be a factor. So just kind of a little aside there. If you're looking to work on those kind of mental math skills, actually kind of strangely, Duolingo, the app that does language learning, actually has a math option for one of their quote languages. And it is a lot of just kind of going through and doing mental math and kind of number sense stuff. And it's actually done quite well, I think. So if you are looking for some practice on that, it's a fun, gamified way to do that. And you can add the math language or whatever, and, do 2 lessons each morning for, I don't know, 90 seconds each or something. And, and just encountering that every day can help you build up those skills. So just a little aside. Okay, so we did 1, 2, 3, 4. Is there a factor of 5? No, again, I got my prime factorization because this was a bigger number, and I see that there are no factors of 5 there. So moving on. 6, well, of course, 6 times 16. 7 is a prime number. I don't see any 7s in the prime factorization, so no 7s. 8 is 2 cubed. That leaves me with 2 times 2 times 3, or 12. So 8 times 12. 9, well, 9 is 3 squared. I only see one factor of 3 in my factorization, so 9 is not a factor. 10 has a factor of 5. That doesn't work. 11's prime. There's no 11s in the prime factorization. That doesn't work. 12, we're back to 12 times 8. So we've exhausted all of our options here. So we've kind of got the size of our numbers right. Now what about the signs? We need to have opposite signs, because AC has to be negative. We also need to add to a negative, which means the larger sign, or sorry, the larger number has to have the negative sign. Negative on the larger number. So here my n's are going to be negative. My m's positive, and I'm looking for one that adds to negative 46. And I think that is this one. Negative 48 plus 2 does give me negative 46. So again, this was a bit of a long and tedious process. Maybe with the guess and check, you would have gotten lucky and gotten it on the first couple tries and saved yourself some effort. But also maybe on the guess and check, you would have spun your wheels for a very long time and it would have become really cumbersome and really frustrating. So going through a method like this for more complicated problems is probably the better way to go. Even though sometimes it can take a little longer than guess and check, I think kind of on average, you save yourself time, and I think you definitely save yourself frustration. So again, we did all of this for what purpose? To figure out that we can break up minus 46x into plus 2x minus 48x, and that'll be just the right way to break up this middle term so that we can do our factoring by grouping in the next couple of steps. So I have 6x squared. I'll do minus 48x plus 2x minus 16. If you did it the other way, no problem. If you did plus 2x minus 48x, that works just as well. The intermediate steps will look a little different, but your end result will be the same as mine. And then again, we want to look at these first two terms and these last two terms. From each of those sets of two terms, factor a greatest common factor. I see there's a factor of 6 as well as a factor of x. 6 times 8 is 48. There's a factor of 2 in the last two terms. And then again, the super important thing to realize here is that breaking these middle two terms up in this specific way is what makes me end up with the same common factor that I can then factor out again. You could factor negative 46x into negative 50x plus 4x. That would be fine to do. You could break it up that way. But then you wouldn't be able to factor and then factor again. You might be able to factor a greatest common factor out, but you might end up with like an x minus 7 and an x minus 4 or something, and that you can't then factor out again. So that's the really important part here, is we're doing this whole process to figure out how to break this middle term up in just the right way, that we now have this x plus 8 that can x minus 8 that can factor again. Now, something that we haven't really talked about so far, and that we're really going to talk a little more about next time, is the idea that we might want to kind of completely factor something, right? There might be like a factorization step that we do, but we might be able to do even better than that. So something I might realize here is, well, if I look at x minus 8, that's like just kind of what it is. There's nothing much more I could do with that. But if I look at 6x plus 2, I actually noticed that with 6x plus 2, that has a common factor of 2 in both of those terms. In other words, 6x plus 2 can be rewritten as 2 times 3x plus 1. So there's actually another common factor that I can factor out. I could write my factorization as 2 times x minus 8 times 3x plus 1. And that, in a sense, would be even simpler. So this is something that we want to start getting used to doing, is when we factor and we think, okay, I think I'm done, take a look at each of your factors and ask if any of them can be factored more. Can we factor a greatest common factor out? Is any of them, or do we still have a quadratic somewhere, not in a problem like this, but maybe in a different problem? Is there still a quadratic that we could, a second degree term that we could try to factor again, something like that? In this case, there was an extra factor of 2 that we could factor out. Now, something we might have realized at the very beginning, we might have realized, if I can get my red pen here, there we go. We might have realized that, say, for instance, each of our coefficients, 6, 46, and 16, they were all even numbers. Let me just copy this down below. I might have noticed these were all even numbers. And I could have actually factored a 2 out in the first place. So this would have given me 3x squared minus 23x minus 8 left over. So if I recognized that at the beginning, I could have factored the 2 out. And then what would I have gotten from the AC grouping method? I would have gotten that A times C equals 3 times negative 8, or negative 3 times 2 times 2 times 2. What would my M and N be? I'm not going to go through all of the details, but we'd have had 1 times 24, 2 times 12, 3 times 8, 4 times 6. 5 doesn't work. 6 goes to 6 times 4, and we're back to a repeat. So I can see that my numbers are a lot more manageable, right? Basically, I eliminated not just one, but actually 2 of these factors of 2. That made the number of possibilities for M and N a lot smaller, and just the numbers were smaller, so they were more manageable, easier to handle. If I recognize something like this, sometimes I can save myself quite a bit of time and hassle by factoring out a greatest common factor at the beginning of the problem instead of only seeing it at the end. Now, if you didn't see it at the beginning, you can see the AC grouping method still works. All of our methods still work just fine, but they're more cumbersome, right? If I recognize that there's that common factor of 2 everywhere that I can factor out first, this polynomial, this quadratic, is a lot easier to factor than factoring this one directly. So one thing that we want to get used to, now that we're a little bit in the swing of things as far as factoring polynomials, we want to get used to using our tools in some sense in the right order. So I could factor the trinomial and then look for common factors. But if I look for common factors first, that can save me a lot of hassle factoring my trinomial. So typically what I'm going to want to do from this point forward is, the first thing I'm going to do is I'm going to look at my terms, and I'm going to say, is there a common factor that I can just factor out from the beginning? If there is, I'll start by factoring that out. And then I'll move on to questions about, can I use the AC grouping method? Can I use the method for just x squared plus bx plus c? Can I use my special products formulas? Things like that. So that's something we want to get used to from this point forward. Okay, so take a look at these 3 problems. Again, work through them kind of as an exercise. We'll take probably about 6 minutes to work through these 3, and then we'll come back and discuss the answers. So take about 6 minutes, and we'll discuss them. Okay, let's look at the solutions to these three problems. And remember, these were, intended to be the more challenging problems from section 3. So this was kind of the wrap up, the end of last class. Um, so these aren't the easiest problems in that section, definitely. So starting with 12x squared minus 41x minus 11, we see that a times c equals 12 times negative 11. Or if we factor that to make it a little easier to find our m and n list, we see that's negative 2 times 2 times 3 times 11. And as an aside, I note that there are no common factors I can factor out at the beginning here. 11 is a prime number, so the only thing I could maybe potentially factor out is an 11. But of course, 11 doesn't go into 12, so greatest common factor is just 1. If I set up my list m and n, m can be 1, which would make n 11 times 3 times 2 times 2, or 132. If I use one factor of 2 for the m, that leaves me with 2 times 3, or 6, times 11 is 66. 3 times 44, 4 times 33, 6 times 22, and 11 times 12. I note that a times c is a negative number, so these have to have opposite signs for m and n. And I note that b is negative 41, so I need their sum to be negative, which means the negative sign has to go in the larger number. The way we set it up here, those are the n's. So I put the negatives on the n's, and then the m's all get positive signs. And I'm looking for one of these lines that sums to negative 41. And it looks like this one here, plus 3 minus 44. So positive 3, negative 44, those are the two numbers that multiply to give me negative 132, negative 12 times 11, and add to give me negative 41. So I can break up this middle term, negative 41x, as negative 44x plus 3x. And then again, if I think, and if you did plus 3x minus 44x, that's fine as well. You'd end up with the same factorization, slightly different intermediate steps, but same end result. I kind of regroup these into the first two terms and the second two terms. I can factor a 4x out of the first two terms, leaving me with 3x minus 11. And the second two terms are actually just 3x minus 11. Nothing really factors out of those. But I'll choose to write it as plus 1 times 3x minus 11, just to make it very clear that next I'm going to factor out this common factor of 3x minus 11. And when I factor that out, I get 4x plus 1 times 3x minus 11 as my factorization. For the next problem, 2x squared plus 4x plus 3, this is actually pretty straightforward to come up with my list of m and n. I know that a times c, 2 times 3, is 6. So I'm looking for two numbers that multiply to 6, but that add to 4, that add to b. My possibilities for m and n are 1 and 6, or 2 and 3. I know they have to be the same sign so that their product is positive. They have to add to a positive number, so they've got to both be positive. So I can just leave them as is. All of my m and n's have to be positive to have a shot at this, but I see their sum is either going to be 7, which isn't 4, or it's going to be 5, which isn't 4. There's no way to break up this middle term in such a way that I can do this AC grouping process and get a factorization. This quadratic expression is prime. It can't be factored. Can't be factored over the integers anyway. And then lastly, we'll finish working through this problem. I see a times c is 4 times 6, or 24, or we can say that that's 2 cubed times 3. I'm looking for two numbers, m and n, that multiply to 24 and that add to 15. I could have 1 and 24, 2 and 12, 3 and 8, 4 and 6. They need to multiply to positive 24, so these need to have the same sign. they would need to add to a positive number, so they need to both be positive. And do I have any line that adds to 15? Well, we have 10, 11, 14, and 25. Again, none of these work. There's no way to break up this middle term 15x in such a way that it lets me proceed with the AC grouping method and get a factorization. This one is also prime. Again, using guess and check, problem 2 would have been kind of tough to tell that it was prime, but we probably would have realized it pretty quickly because we can only break it up as a 2x, potentially 2x and x. And then we either have to have plus or minus 3 and plus or minus 1 here, or the other way around, plus or minus 1 and plus or minus 3. So there just weren't a whole lot of options to try. And it's pretty easy to see from looking at the problem that these are the only options, and I could exhaust them pretty quickly. This one, right, this would have been a nightmare to guess and check, to try to work through all of those different 1 and 4 versus 2 and 2, and then 1 and 6 versus 2 and 3, and all those different combinations. But again, the AC grouping method gives me just a series of steps to follow that either gets me the answer of what the factorization is, or confirms that there's nothing in this list that's going to work. There's going to be no factorization over the integers. Any questions on anything from really either 7.2 or 7.3, this kind of general strategy for factoring trinomials? Remember, the common theme in both 7.2 and 7.3 is we are looking for two numbers m and n that multiply to a certain number and that add to a different number. In 7.2, that kind of gives us our factorization right away, where we get two numbers that multiply to c and that add to b. That just gives us our, x minus m, x minus n. Sorry, x plus m, x plus n. Thinking of the wrong thing. We're thinking of solutions, which we're about to move into next class. And then 7.3, we had actually that's a similar strategy with the AC grouping method. We're looking for two numbers m and n that multiply to a times c and that add to b. But here, m and n don't give us our factorization straight away. M and n tell us how to break up this middle term. And then we can proceed by factoring by grouping. Moving into 7.4, we're taking we're kind of shifting gears a little bit. We're taking a different approach. We're saying there are times that we might recognize the form of a certain quadratic expression, like this one or like this one, say, and we might have a bit of pattern recognition. We might know that there are special cases where we recognize a certain pattern, and then we can just apply a formula. Sometimes we can avoid all of this, AC grouping hassle or all of that by recognizing a certain pattern that I've seen before and that I know how that pattern factors. So we have three of those patterns we're going to look at. The first one is a perfect square. So when we were talking about operations on polynomials, when we were talking about multiplying polynomials, we remember that a binomial squared has this kind of a pattern. A plus or minus b all squared is a squared plus or minus 2ab plus b squared. Whether the inside sign here is a plus or minus, this b squared always ends up with a plus, because even if it was a minus b, that minus b is being multiplied by another minus b when we do our lasts in FOIL, so the minuses cancel. So the square terms, the a squared and the b squared, always have a plus associated with them. And this middle term, this cross term as it's sometimes called, the one that has both kind of the a and the b appearing in it, it shares the sign that connects the a and the b. As kind of an interesting little side note, note that say for instance, a minus b all squared, you might say, wait, a minus b all squared is a squared minus 2ab plus b squared, but that's kind of symmetric in a and b. Shouldn't the negative be somehow inherently attached to the b? Well, note that a minus b all squared is the same as b minus a all squared. When I note that there's a symmetry, I might want to look a little bit deeper. When I notice that a minus b all squared is a squared minus 2ab plus b squared, if I swap the roles of a and b on the left, nothing really changes. So is it true that if I swap the roles of a and b on the right, nothing changes? Well, that is true. And why is that? Well, it's because a minus b equals -1 times b minus a. So a minus b all squared is -1 times b minus a squared, or that's -1 squared b minus a squared. But of course, -1 squared is just 1 times b minus a squared. So we see a minus b squared is the same as b minus a squared. Interesting little tidbit there. I think these are some of those things that, you might look at the pattern 1,000 times and never see it, and then the 1,001st time you look at it and you see it and you think, wait, has that been there the whole time, and why does it work that way? And it seems to kind of break everything until you sit down and really think about it. Okay, so let's take a look at this example: 49x squared plus 154x plus 121. I suppose I could go through the AC grouping method, but these numbers are pretty big. That's probably going to be kind of messy. I look for a greatest common factor. Well, 49 is 7 squared and 121 is 11 squared. So there's no common factors between even the first and third term, let alone worrying about the middle term. But one thing I did notice when I was thinking through my couple of terms is that this first term is 7x all squared, and this last term is 11 squared. So I noticed that 2 of my 3 terms are perfect squares. So I noticed that I have this bit of the structure already. And then typically what I do is, that usually I recognize the pattern by recognizing these squares, these perfect squares. And then I have to ask the question, does my middle term actually match up? Sometimes it does, sometimes it doesn't. If my middle term doesn't match up with what I'd expect it to be under the perfect squares pattern, it's not going to factor as a perfect square. It might factor a different way, or it might be prime, but it's not going to factor as a perfect square if that middle term doesn't match up. So I have to check the middle term. So I know that I would have A being 7x up here, B being 11. And then my question is 154x equal to 2ab with a plus or a minus? In other words, is it equal to 2 times 7x times 11? Well, that's 14 times 11. That is 154x. So it is. I recognized my first and third terms as perfect squares. I checked, and my cross term does match this 2ab pattern. So I note that this quadratic expression does fit this perfect squares pattern, and it's going to be 7x plus 11 all squared. When I FOIL this out, my first give me 7x times 7x, or 49x squared. That checks out. My last give me 11 times 11, or 121. That checks out. My outside, I'll write it out just so we can keep track of what's going on. My outside gives me plus 77x. My inside gives me another plus 77x. Adding those two together does give me plus 154x. My cross term does match. So I do see that this is a perfect square trinomial. If I look at this next example, I first look for a greatest common factor, but I see that 64y squared, 64 has a bunch of factors of 2, and that's all. And then I have a factor of 1 here. Of course, there's going to be nothing that I can factor out at the beginning. But I do note that 64y squared is 8y all squared. And I do note that 1 is 1 squared. Now I might jump ahead and start asking questions about 2ab and so on. But before I do that, does this fit the perfect square pattern? Remember that the terms that are squared have to always have a plus associated with them. This one actually has a minus associated with it. This minus being associated with the 1 here is enough to say this doesn't fit the perfect square pattern. So as it stands now, we wouldn't be able to use perfect squares on this problem. We might try something like the AC grouping method to see if we could get a result that way. However, for sake of continuing on with the problem, let's suppose that we had a plus here. Now, does it fit the perfect squares pattern, at least at first glance? And yeah, now it does seem to. So very important that I check the signs on my squares and make sure they're both positive. Now they are both positive. Now for this problem, I could proceed forward. Just to be really clear, like 2 different problems. So this problem, if this problem was given to you, you can't proceed forward with the perfect squares. But the only reason I changed the minus to a plus was just to demonstrate how important that is, that we check that positive sign. So this would be like a new problem. I didn't do some mathematical operation and change the minus to a plus, just different problem. In this case, we can proceed forward with perfect squares. So here I would have A being 8y and B equals 1. And then my question is negative 16y equal to plus or minus 2ab? Or is it equal to negative 2ab? We see a and b are both positive, so to get negative 16y, we'd need to be looking at negative 2ab. So is this true? What's negative 2ab? It's negative 2 times 8y times 1. And yes, that does give me negative 16y. So 64y squared minus 16y plus 1 is a perfect square. And I see that I have a negative 2ab cross term. So my square is going to be a minus b squared. It's going to be 8y minus 1 squared. This minus is what gets me that minus and that minus. And again, if I check, my first give me 8 squared times y squared, or 64y squared. That looks good. My last give me minus 1 times minus 1 is a plus 1. That looks good. And my inside and outside give me minus 8y and another minus 8y and minus 16y. That also looks good. And we could even have more complicated looking examples like this, where I have even 2 different variables in play here. But I still do notice that 25r squared is 5r all squared. 36s squared is 6s all squared. So I could have, say, a equals 5r, b equals 6s. And then my question is, is negative 60 RS. Is that equal to negative 2 AB? Right here, A and B are both positive. So to get a negative sign here, I need to be talking about negative 2 AB. Right, that's my cross term that I need to check here. Or is that equal to negative 2 times 5R times 6S? Well, that's 5 times 2 is 10, times 6 is 60, negative 60 RS. And yes, that does match. Since that cross term matches, I do have a perfect square trinomial. And this is going to be, I had to use the negative 2AB option. So this is going to give me A minus B, 5R minus 6S, all squared. And again, if I check my firsts, 5R times 5R is 25R squared. That looks good. My last 6S, sorry, negative 6S times negative 6S, negatives go away. We get 36S squared. That looks good. My outside, I have 5R times negative 6S. That's minus 30 RS. And my inside, I have the same thing, minus 30 RS again. That's minus 60 RS. That all looks good. And I don't think I mentioned it, but there was no greatest common factor to factor out at the beginning either. 25 is 5 squared. 36 is 6 squared. No common factors there. Okay, so take probably about 5 minutes to work through these three using that perfect square. And let me actually move the formula over here for you. Using this perfect square formula, this way you have it right at hand. Take about 5 minutes to work through these three problems. See if you can match it up to a perfect square and see where you can go from there. Okay, let's look through these three problems. So the first two I think are pretty straightforward. The first we want to factor 25x squared plus 20x plus 4. We note that there are two terms that are perfect squareds with positives attached. So 5x squared and 2 squared for the first and last terms. This would mean our kind of candidate form for the perfect square is where a is 5x and b is 2. And then we ask, does the cross term meet the pattern? Is it true that 20x equals 2ab? Here I know I'm looking for plus 2ab because 20x is positive. Does 20x equal 2ab? Well, we plug in a and b, we multiply out, and we do get 20x. Yes, it does match the pattern. The 2ab was the plus 2ab that we were looking for, so we see this is going to factor as a plus b squared, 5x plus 2 all squared. And we could check our first 5x times 5x, 25x squared. Our last 2 times 2 is 4, so first and last work. My outside is 5x times 2 is plus 10x, and my inside is also plus 10x, so plus 10x plus 10x is plus 20x. So this does check out. Similarly, for our second example here, we note that 4y squared is just 2y all squared. 169, we might have to think through what's the factorization of that. But that's 13 squared. So I recognize that I have two terms that are perfect squares that have positive coefficients or that have plus signs attached to them. And then my question is, so far I match the perfect square pattern, but I have to check this cross term. Is it true that negative 52y equals negative 2ab? I see a negative 52, so that's why I'm looking at negative 2ab. So what's negative 2 times 2y times 13? That is indeed negative 52y. That does fit the perfect squares pattern. So I factor this as 2y minus 13 all squared because of the minus in front of the 2ab. And if I check, my first give me 2y all squared or 4y squared. My last give me minus 13 times minus 13 is positive 169. My outside gives me 2y times negative 13. That's minus 26y. My insides also give me minus 26y. So minus 26 plus a negative 26 is negative 52. Negative 52y is exactly what I was looking for the cross term. And the third example down here, sorry, it's a little smashed together. I was trying to get everything on the screen. 100r squared minus 25rs plus s squared. This does seem to fit the perfect squares pattern. I see I have the a squared and the b squared. I have two terms that are perfect squares with positives attached, 10r all squared and s squared. That's a pretty simple one for b. So if a is 10r and b is just s, does the cross term work out? Negative 25 rs. Is negative 25 rs equal to negative 2ab? Or is it equal to negative 2 times 10r times s? Well, that's negative 20 rs, not negative 25 rs. My cross term does not work out. This does not fit the perfect square pattern. I cannot write this as something like 10r minus s all squared. Does that mean it doesn't factor at all? Well, no, not necessarily. It just doesn't factor as a perfect square. How might it factor? Well, we might think back to our previous couple sections. And we saw before that if I have a pattern like this, I can kind of ignore the r's, and I can look for an m and n that multiply to 100 and that add to minus 25. So that might be like 1 times 100, or 2 times 50, or 4 times 25, or 5 times 20. Well, hey, that looks promising. Or, of course, 10 times 10. I need them to multiply to a positive number. They could both be negative. And this is a section 7.2 example. So I think this is going to be like s minus 5, which my s unfortunately looked kind of like a 5, and s minus 20, more or less. But remember, I kind of left the r's out. Where would the r's go? Well, the r is just attached to the constants. So I'd have s minus 5r, s minus 20r. My firsts give me s squared. My lasts give me minus 5 times 9 minus 20 is plus 100 r squared. That works. My outside gives me minus 20 rs. My inside gives me minus another 5 rs, minus 25 rs. So we actually do get a factorization. It's just not a perfect square, even though at first glance, looking at these two terms, it kind of looked like it might be a perfect square. And the cross term didn't quite turn out right. It didn't end up being a perfect square, but it did end up factoring. Or we could also have a situation where it's not a perfect square and it doesn't factor in the integers. It just turns out to be prime. That would be another possibility. Or of course, if instead of having a negative 25 rs, if we had a negative 20 rs, then it would have been a perfect square. So things that initially look like the perfect square pattern, where I see that I have two terms that are perfect squares with pluses attached, it could be a perfect square, could be not a perfect square but factor a different way, could be a prime and not factor at all, essentially. Okay, and then the last pattern that we're going to take second to last pattern, two more patterns to take a look at. The next pattern is the difference of squares. Getting ahead of myself. I was thinking we're already at the cubes, but the next pattern, difference of squares. And this is one, again, that we had talked about before when we were multiplying polynomials. We said a plus b times a minus b equals a squared minus b squared. Factoring going the other direction, this is going to be a very useful pattern to be able to recognize the difference of two squares. If I have only two terms, if both terms are perfect squares, and if one of the terms is the opposite sign of the other, if one of the terms is negative and one is positive, then I have this difference of squares pattern. If I look, for instance, at something like this, 169y squared minus 1, this is 13y all squared minus, well, 1 is just 1 squared. So 1 is a perfect square. 169y squared is also a perfect square. I see I have a difference of two squares. There's nothing else I need to check here. This is just going to be 13y minus 1 times 13y plus 1. What's kind of the magic here? Why do we only end up with two terms when we multiply out instead of three? Well, if I multiply out, I get 13y all squared. That's this bit here. My lats give me minus 1 squared. I get a minus 1 times a plus 1, so that is a net negative. And then the size of the number is 1 squared. So that's this term. What happens to the outer and inner? My outside is plus 13y times 1, and my inside is minus 1 times 13y. These two perfectly cancel. My outside and inside perfectly cancel. They perfectly go away. My cross terms disappear. So the difference of two squares pattern, again, if I see two terms and only two terms, where both terms are perfect squares and where they have opposite signs, that's the difference of squares pattern. If I have something like this, 49x squared minus 81y squared, I recognize this as 7x all squared minus 9y all squared. we can see between this example and the previous one, it's important to be familiar with our perfect squares. So if you're not familiar, write them down and have them on a slip of paper beside you while you're going through the homework problems, and that'll be helpful. But I recognize 81 is 9 squared and 49 is 7 squared. And I do see that I have exactly two terms. Each of the two terms is a perfect square, and they're opposite signs, right? They're connected by a subtraction. And I see that this is going to be 7x minus 9y times 7x plus 9y. And just as a quick aside, I know that I've mentioned this before, but just a reminder, if you wrote your answer as 7x plus 9y times 7x minus 9y, that's the same answer, right? When we say a factorization is unique, we mean unique up to ordering of the factors, because multiplication is commutative. Either way you write it is just as good as the other way. If we look at something like this, we might say, oh, that's not a perfect square. And neither one of those terms are perfect squares. 98 isn't a perfect square. 72 isn't a perfect square. We don't even have, like, our factors of r aren't even perfect squares. But something we want to keep in mind, it's related to this idea up here, that it's always useful to look for a greatest common factor first. I haven't seen a greatest common factor in any of these problems recently. But if I just glance at this, I say, oh, not a difference of two squares. Example, none of my terms are perfect squares. But I might realize, okay, I can actually factor out a greatest common factor first. I actually notice that there's a factor of r everywhere. 98 and 72, well, they have a factor of 2, I suppose. So what's my greatest common factor of 98 and 72? What would I do? I'd write 98, 72. Well, 98 has a factor of 2. It's 2 times, what, 49? So 2 times what? 7 times 7. 72 has a factor of 2. It's 2 times 36, or 2 times 6 times 6. And remember, to get my greatest common factor, I write down any number that exists in the whole column. So I see that both rows have a 2. The 72 is missing 7s, and the 98 is missing 6s, so I don't write anything else. There's a greatest common factor of 2 as well. 98 is 2 times 49, or 2 times 7 squared. And I'm left with two factors of r, minus the r comes out, and 72 is 36 squared, or 36, or 6 squared. Now I see that this is 2r times 7r all squared minus 6 squared. I recognize that after I factor that greatest common factor out, I do see a difference of two squares pattern. So sometimes the pattern doesn't reveal itself until after you factor out a greatest common factor, and then it becomes obvious. So here I have, in the parentheses, I have two terms, exactly two terms. Each term is a perfect square, 7r all squared and 6 squared, and they have opposite signs. And so that's how I would factor this one. Getting that greatest common factor out here was really crucial. It helped a lot in the previous example, but it was more a question of saving time and hassle. But here it was really crucial for me to be able to recognize the pattern. So let's work through a couple of these examples. And again, I'll pop the formula over here for you. So I have 3 examples here, and then also kind of a challenge example here at the end. So try to work through that one as well. Let's take about 5 minutes or so. The first 2 should go pretty quickly. and then the last two might take another couple minutes. So we'll take about 5 minutes, come back together and discuss. Okay, so let's look through these problems. The first two, again, I think were pretty straightforward, especially if you realize that 121 is 11 squared. So y squared minus 9, pretty clearly that's y squared minus 3 squared. So we have exactly two terms. Both terms are perfect squares, and they have opposite signs. This gives me y minus 3 times y plus 3. 121x squared minus 25y squared. Again, exactly two terms. Each term is a perfect square, 121x squared being 11x all squared, and 25y squared being 5y all squared. And they're opposite signs, so I have 11x minus 5y times 11x plus 5y. The third one, again, I kind of look at it and I say, well, I mean, I have two terms, but 24 is not a perfect square, 54 is not a perfect square. But I do notice that I can factor out a greatest common factor of 6. 6 times 4 is 24, and 6 times 9 is 54. So factoring the 6 out leaves me with 4y squared minus 9. And I do realize that 4y squared is 2y all squared. 9 is 3 squared, so I have exactly two terms. Both are perfect squares, opposite signs. So that part in parentheses can be factored to 2y minus 3 times 2y plus 3. And we still have that factor of 6 in front. Kind of as an aside, when you factor out a greatest common factor, at least I find that I can occasionally make the mistake of like forgetting about it because I'm paying so much attention to what I'm doing with all of the stuff inside the parentheses. I can forget to just bring that along with me. So that's, one thing to just make sure that when we go from one step to the next, that we make sure that we carry along any extra vestigial stuff, even if it's not part of what we're most proximally working with. And then for the challenge problem, this is challenging for a couple reasons. First of all, we might not immediately think of, say, a fourth power or a sixth power as being a square because it doesn't have a 2 explicitly in it. But really, x to the fourth is x squared squared. And y to the fourth is y squared squared. So these actually are two terms that are both squares. And because they're connected with a minus, they do fit the perfect squares pattern, or sorry, the difference of two squares pattern. I see that this factors into x squared plus y squared times x squared minus y squared. But I also notice that I'm left with quadratics. I'm left with second degree polynomials. I might be able to factor one or both of these a bit more. And I actually noticed that x squared minus y squared is a difference of two squares if it's the same pattern. It has exactly two terms. Each term is a perfect square, x squared and y squared, a little more obvious this time, and different signs. So I see x squared minus y squared factors into x plus y times x minus y. That came from the second factor. What about x squared plus y squared? Well, that one's not going to factor. This is kind of like x squared plus 1. Remember, when we have kind of this type of pattern, like x squared plus something xy plus y squared, we can kind of, roughly speaking, ignore one of the variables at first. And if I'm looking for two numbers that multiply to 1, but that add to 0 so that the cross term, the linear term, goes away, I can't think of any two numbers that multiply to 1 and add to 0. I either need to have 1 times 1 or -1 times -1. Neither of those add to 0. Now, of course, if this was a -1, plus 1 times -1 multiplies to -1 and adds to 0, and that's why that worked in the difference of squares down here where there was a minus. But in the plus 1, we see that that's not going to work. So we just have x squared plus y squared. This bit is prime. This doesn't factor anymore. But this x squared minus y squared does factor again. Okay, and then in the last few minutes, let's look at the next pattern here, the sum or difference of cubes. So here we have two terms where each term is a perfect cube, perfect third power, and they actually can be connected with either a plus or a minus. There's not a restriction like in the difference of squares where it had to be a minus connecting them for it to work. We just need to have exactly two terms that are each perfect cubes, and we can factor it. So an example would be something like x cubed plus 27. I see that this is x cubed plus, and 27 is 3 cubed. It might be good to know the cubes up to maybe 5 cubed. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. They might be, say, good ones to know for that might come up in these sum or difference of cubes problems. So x cubed plus 3 cubed, I see that I've been careful here. A cubed plus or minus b cubed equals a plus or minus b. So the pluses and minuses are in the same order. So a cubed plus b cubed equals a plus b times, and now note this funky looking sign here, a squared minus or plus. The minus and plus switch roles, ab plus b squared. So for x cubed plus 27, where a is x, b is 3, this is going to factor into x plus 3. We maintain the sign here. A squared is x squared. We switch the sign here, minus. So we switch or invert, whatever symbol you want to put for switching the sign. AB is 3x, and then plus b squared is plus 3 squared, or 9. That's how this is going to factor. It seems strange that it would factor like this. What happens here? Well, x times x squared gives me x cubed. X times negative 3x gives me negative 3x squared. X times 9 gives me plus 9x. And now I distribute my 3. 3 times x squared gives me a plus 3x squared. 3 times minus 3x gives me a 9 minus 9x. 3 times plus 9 is plus 27. And I see I get this kind of miraculous cancellation of my middle terms. I end up with x cubed plus 27, which is exactly what I had hoped for. My middle terms cancel. You can memorize this formula. Personally, I don't like memorizing formulas where the signs are really important, where having the plus and minus in the correct place is really important, because it's easy to get a little mixed up, a little jumbled up, get a plus where a minus should be or vice versa, and that completely throws you off. So I like to kind of understand the pattern. I understand that when I have a sum of two cubes, I can factor out a plus b. And when I have a difference of two cubes, I can factor out a minus b. And then I also know that what's left over is going to look almost like a perfect square. Note that it has 3 terms, 2 of which are perfect squares, but the cross term is not 2ab plus or minus. The cross term is just ab. So this actually will not factor. This will not factor any further once we get to this quadratic bit. This a squared minus or plus ab plus b squared. Once we get there, it doesn't factor any further, and we know that as just a property of cubics. So if I didn't have the formula right here, how would I approach this? Well, I would say x cubed plus 27, plus 27. I know that's got to be like x plus 3 times something. I know that I've got to have something that gives me an x cubed when I distribute, so this has got to be an x squared, obviously. So that when x hits x squared, that's where I get my x cubed from. Let me give myself a little more space here. I also know that 3 times something needs to give me my 27, my constant term. 3 times 9 is going to give me my 27. This clearly has to be a plus. My squareds both have to be pluses. My squared terms in the second parentheses. And now I need to figure out what's my cross term. What's my middle term here? Well, what's the stuff? So this is good and this is good. Those are things that show up in my final result. But what are the bad things in some sense? I mean, maybe we shouldn't ascribe moral character to math expressions, but I don't know. The bad things in a sense are the 9x. I don't want that persisting. I don't want that to show up in my final answer, and the 3x squared. So I've got to get rid of those. So I need to get rid of a 3x squared. If a minus 3x hits an x, that gives me a minus 3x squared to counter the plus 3x squared. And then when minus 3x hits the 3, I'm kind of pulling a John Madden here, scribbling everywhere, but when a minus 3x hits the 3, that gives me a minus 9x to counteract that extra plus 9x that I want to get rid of. So this is how I like to do it. I remember that if I have the sum of two cubes, a plus b factors out, and if I have a difference of two cubes, a minus b factors out, and then I just kind of work it up from there using kind of just puzzle solving almost. That means I don't have to remember the formula. I kind of remember the general idea that sum of two cubes, the sum of the numbers factors out, and difference of two cubes, the difference of the factors or the bases factors out. And then I kind of figure out what I need to get first the terms that I need to end up with. How do I manufacture those? That's going to leave me with some extra stuff that I want to get rid of. And then how do I get rid of that stuff? So you can either memorize the formula, or you can kind of take this slightly more abstract, more generalized approach. But either way, I get to x plus 3 times x squared minus 3x plus 9. And again, I just remember as a math fact in a sense that when I'm factoring difference of two cubes, this bit that I'm left over with won't factor any further. That's just what it is, x squared minus 3x plus 9. I don't have to look any further into that. I don't have to do my m and n and everything to prove that. It won't factor any further. I know that it's a property of this setup that will not factor any further. So at this point, I'm happy. I'm finished. When we come back, we'll do a couple more examples, work through a couple examples, and then we'll also, when we come back, take a look at, I think the book calls it like mixed practice. So when we were in a certain section talking about difference of squares, we kind of know we need to use difference of squares, but what if I didn't tell you what section we were in? That's a step up in the level of challenge, right? Because if you don't know which formula to use, you have to, number one, figure out which formula to use and then apply it correctly. So far, we've known which section we're in, so we know which formula to use, and it's just a question of applying it correctly. So that's what we'll start out with next time, and then move on from there to general kind of factoring strategy and solving quadratic equations.